啊，基督教的这句话里面就不否定一切都存在。
没对啊，有啊，那猪都给那鬼上身了，他不是赶那个猪跳海跳河吗？记得吗？
我没有点忘了。
要找一个猪跳海的那个故事，你不懂？不懂？你知道不懂？
哪本书？
好像是在新约，那魔鬼上那个猪的身体。
但是这个有一本书叫《梦之钥匙》，可以去看。梦之老师的钥匙。
你看鬼就要求太买太发展上面，鬼就要求耶稣说：若把我们赶出去，就打发我们进入猪群了。然后耶稣说：去吧，鬼就出来进入猪群，然后全群突然闯下山羊头在海里面死。
哦，
啊，哎呀，耶，刚刚怎么说？
带上来，幼稚嘛，
孩子
那题
啊，就是他们要给那个我没有带，应该希望他们有带。去，我没有带纸。哦，我这边有那种纸，那种。我就在想，我要不要带那包东西上来？我觉得不用带，糟糕了。
你可以啊。
没有，对
学校的书就是他讲的是怎么样？对呀，我那时候补课啊。
啊，
那上次就跟你讲的时候，他进来了一下，然后看到是你就走掉。
没有，
然后多少问题？哎呦，
心里面扣我了吧？你根本是我的看好像有问题。这个 Yeah. That's
Okay. Okay. Last time we stopped with here. Last time Jason say what is the homoism, right? Category, yeah. And okay, and the object is this inclusion and this. Okay, these two objects. Okay, and the most recent is this. And then you have the commute. If can, can, then just it like this lah. Okay. Proposition say we have this. Yeah. Okay. Next. Yeah, next, we talk about the subgroup generated by subset. The definition like this. Why we interest for this like cyclic uh, generated by some subset, because we want to find the smallest subgroup they contain A. Okay. Yeah. Okay. This is the intersection for the hash. Well, the hash is a subgroup of G, which is contain A. Okay. And we call this is subgroup generated by A. Okay, next. Okay, we say this is the a group G is a finitely generated if there exists a finite subset A such that this G equal to generated of by A. This is called finitely generated. And next we talk about the cyclic. The cyclic is the like Z is the example, the example like 2Z. 2Z is mean the multiple of 2. Okay. It's cyclic of 2, which is the element like multiple of 2. Okay. Generated by 2 because you can use every element like 2 times some m inside. Okay. Okay, and then this is subgroup. We want to check now. Okay, this for addition. First is identity 0, and then inverse another one. Okay. Okay. Next, I want to talk the subgroup of cyclic group. Then sub is also cyclic group. Okay, it's a small remark. And next is the proposition. Okay, let G be in Z integer, be a subgroup. Then G is equal to dz for some d greater than or equal to 0. The proof I not say detail, I just do some scratch. Okay, for some idea. Here, like why like this? Because if you say G is subgroup, okay, subgroup, then G either you have identity on it, or G have some other element like G. Okay. Okay. Then if G inside minus G immerse inside out, right? And other G square, G cube, and so on inside. Then this is what? This is like G square is in Z, right? The operation is plus like 2Z, 2G, 2G. Okay. So all of these elements like a multiple of G. Okay, so you can think like this. Yeah, but if G is not 0, okay, if G is 1, then this is Z itself. Okay, if a group contain two different elements, and then you see like example 2 and 3. Okay, then I can generate 1, but 1 equal times 3 plus minus 1 2 like this. Okay, and then I have 1, I can generate all the insects. So this group is also Z. Okay. Idea lah, but the detail is like this. Okay, next. Okay, next is let n be an integer and G is the Z mod and Z be a subgroup. Then G is a cyclic subgroup of Z mod and Z generated by the class of D for some divisor D of n. Okay, also Sam, I don't go detail, I just let you see the example. Yeah, okay. Why is the divisor D? You can see if I take the Z mod 12. And then the subgroups is I want to have this like example 4. 4 plus 4, 8, and then plus 4 go back to 12. Yeah, so I need a divisor. Okay. Then 12 have 6 positive divisor, and then I have 6 subgroup. Okay, 6 cyclic subgroup. Then more detail, right? You can see like 3. How many elements here you can use 12 divide 3 and 4, right? Okay. There's some remark here. If D1, D2 are both divisor of n and D1 divide 2, B2, then the cyclic generated by D2 is a subset of cyclic generated by D1. Okay, why? You can think like D1 equal to D2 equal 4. Okay, D1 divide D2. And you can bring D1 generated by D1 is like yeah. Cyclic generated by 2 is 2, 4 multiple of 2. Okay, but this is multiple of 8, right? This is more element than this. Yeah, so this is a subset of. Okay. This is
Yeah, way to write down is D2 is a multiple of E1.
like you mean E2 equal to multiple of E1.
Everything in the sample generated by D2 are multiple of D. So n times D2 is nm.
Okay, right. Okay, got it. Got it. The detail. Okay. Okay, next. Next, we talk the monomorphism in class already. So this definition, okay, for monomorphism. Then we interest in this three equivalent. This A, if and only if this C is really proof in class, right? Okay. Then why the kernel also only have the identity because injective. So you can one send to send one to one. No one to one injective. One to something identity G prime. Okay. You now have kernel have many element. You can have send to one thing via injective. Okay. The idea is like this are the rigorous proof is here. Okay.
Because morphism to send identity to identity.
Yeah.
And then if it's injective, then that's the only thing.
Yeah. Because kernel, maybe some kernel have more than one element, right? Because this injective only can one.
Because
Injective.
identity is already and you only can have.
Yeah.
And so it must be
Identity. Okay. Thank you. The next is chapter 7. We talk about the quotient group. Okay. Talk about quotient group before. We talk about what is a normal group. Okay, normal is okay. Let's say N is a normal. It's a subgroup of G, and then it's a normal. Then for all G in G, or N in N, G and G inverse is also in N. Okay. There's some remarks here. Every subgroup of a commutative group is normal because a commutative you can change, right? Change, and then this is identity and time and identity is N. Okay, it's obviously lah. Okay, commutative group is normal. There's some remarks here. The lemma say is the kernel is normal. Kernel of this homomorphism G to G prime. Okay, why like this? Because the kernel is send the element to identity, right? If I send to identity, and then this I can combine to identity. So okay, so the kernel is a what normal. Okay, and I don't talk detail okay, because time I scared not enough. There's some remark here. Guys, if a group subgroup is kernel, and then it must is normal. Okay. Then this is some notation definition of the notation GA and AG. This call set and then later we will come. Yeah, okay. Okay. Then another notation for the normal group like this G and G inverse is in N. This is a normal group. The notation. Okay, equal. This you can think like the G inverse go to here. This notation. And next, we talk about the quotient group. The quotient map like this, phi G to G modular to quotient out the relation. Be a group homomorphism if class A is a pi A, class B is pi B, element of the G quotient out relation. Then the homomorphism condition force the class A times class B equal to class A. Okay, the definition. Actually, we want to check the well-defined, but I don't have time. Okay.
And you can comment.
Okay, comment.
Yeah.
Okay. Comment. well-defined how to check well-defined, like we want to check if A prime, okay, we want to check the class well-defined, okay. We want to
Check by definition. I think what you want to check is like class of A and class of B is equal to class of, let's say, A prime times class of B. This is what you need to check. Definition. This one we already know. You want to check because you look at your pi definition, right? Your pi definition is applying on representation and representative, right? So if I change class of A to class of A prime,
if I change class of A time class of A prime.
No. Class of A times class of B.
Okay.
Then you want to check
this is A prime times B. Oh, okay.
Even that you know that A
is this relation.
A. So you don't write that equivalence anymore. You just write equal because that equivalent class are the same.
Oh, okay.
This is if and only if it's by them.
Okay.
Yeah. So you assume A equals to A prime and B equal to B prime and then you prove this.
Yeah. We just use the definition. Okay. So this is G is pi center. Then B, maybe I can change to A equals this. This can this just equal anything. And okay. because this A is equivalent to A prime, right? This is equal to this. And then let me add, so this is equal to A prime. Okay, then this combine, get this, then this equal to this. Okay, 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 okay. Yeah, now we are defined. Okay, next, the proposition is say the operation defined like this, and then if I group structure on G portion of the relation, if and only if for A prime G in G, A relation to A prime implies G A relation to G A prime, then another side. Okay, the proof also, okay, we don't talk detail. But we can see here, I can think like almost like the normal, okay, the normal like we want to talk about this, so we want to use. Okay. Okay. And previous, because we want to we have to check the direction. This direction obviously because just do the well defined same thing. Okay. But you want to come back, you want to define, and you want to show this group, you want to do anything. Okay.
I cannot imagine like how you use the property to prove this function.
How to use
I give the group, but then how you use that? Like the line form, yeah. Well defined. Yeah. Or maybe it's just for well defined. I think. Is it? Why?
I don't hear why you can change like this.
I thought that one is just associativity investment.
Yeah. Maybe here is not used, but this here also use this this what this thing, the group thing here, and then I think it's next part.
Which part use this? Oh, okay, okay. Because you maybe G inverse and E G. Wait, equivalent.
I mean, let's say if the class have this, right? If I have the equivalent relation, I can do quickly like go to times.
How you multiply?
I can do like this. I mean, many things need to do this.
Okay. 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 So basically, right to left is similar to the word.
Yeah. Yeah.
Okay. Okay. So right to left is just help you to multiply.
Hmm. Okay, next is we talk about equivalent relation. If the equivalent relation is satisfying this, then the equivalent class is of G of identity is a subgroup, and then this A equivalent to B if and only if A must be in H, and then AH equal to BH. These are more like left coset. Okay. Okay. These are more important. Concept property. Yeah, concept property. I think maybe I think it's how to get this. Let's see how to get this again. Okay. Oh, okay. Before we can see this A and B is equivalent to identity, and B inverse also equivalent to identity because we say just now the equivalent class is identity. Okay. This just now. This I think is okay like this. And then proof subgroup we before no. In front we have show this. We show A B inverse in H. Then we can prove the H is subgroup. Okay. And the next thing is we already have this. This is and this okay. Like same thing is like this. We take the inverse of A and then it times together is equivalent to identity. Then this is in H. So we get this. And most is obviously is now we define the left concept and right concept. The left concept just we take the element in G. If left concept we just set like this AH. Okay, if a right concept of H, we just put the HA like this. Okay. And next proposition is say the we have two notation like this relation left and right. Right. Next thing. Okay. Left first this thing we say above left. Okay, and H is a subgroup, and then the relation is defined by like here. A must be in H. It's an equivalent relation satisfying the left. Okay, left to the left to the reverse equivalent. Okay. And this is the left, right? We can do. This is the definition. Define. Then this implies we can take this is a G must G is between them identity. And then we just switch this to inverse and get this relation. Okay.
Why is it L?
L is like a notation for the left side left side. And R is a right X. Okay, and next is we define the partition. Okay, with the equivalent left and right concept. Okay, This partition is a set of set. Yeah, this left is we take the AH, and this right we take the HA. So A is in G. Okay. Okay, we say the relation these two is corresponding to a subgroup coincide. Coincides mean same equal. Okay, coincide same. Okay, if and only if H is a normal. If this is equal, right? Then I have for all G, GH equal to HG because coincide same thing. Here is same. Okay, for every G. Then the same this before we say the notation like this is normal. The H is normal.
What do you mean the relation equal?
Relation coincide. Coincide mean the element here is same as.
But then you should write G quotient. You should write G quotient L. I mean, you should write G quotient L.
Here.
Yeah.
Okay. You mean like G quotient equal to G quotient.
Yeah.
Okay.
And then this coincide doesn't imply that every element.
Oh.
You understand what I said?
Alright. Okay.
That one actually requires proof. They just say that the two set is the same. You understand what I mean?
You mean like,
not the exactly G is the same.
Oh, you mean like they have two only some G?
Maybe A1H equals to HA2.
Oh, okay.
Because it just say two set coincide, right?
Okay. You mean maybe they have some G1H equal HG2.
Yes.
Okay.
How do you show that G1?
Now, let me think. G.
I think this one is an exercise.
Okay. Let me add inside a letter.
Yeah.
Okay, let me add inside. Let me do some. Okay. Thank you. Yeah, next, next is a definition, and let H be a normal subgroup, and then the quotient group G modular H. We did not like this. Then it's a group obtained from the relation defined as AH equal to HA. With these two set equal. Then let's see only the left concept. We can do like this. AH and BH is ABH. Later we want to use. Okay, we want to use this. Very important is. Right also something HA times HB is HAB. Yeah. Then the identity element of this is EG H. Okay, equal to H. Yeah. And next is a theorem. The theorem say like this: the H is a normal. Then for every group homomorphism phi go from G to G prime, then H is in kernel phi. There is a unique group homomorphism this phi to okay. So that the diagram like this commute. Yeah. The idea like this. We take an example. Yeah. We take the G is Z and then G prime is a Z6. And Z6 means we send the N to the N mod 6. Okay. I will take example to discuss. I don't go detail. Okay. 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 What's this thing to do? This is in the kernel, right? The kernel of H, we can think like the Z, because the Z normally is 1 to infinite minus Z is 6. That is normal is this. Then we take the kernel. The kernel is, we go here, the kernel is a 0, right? A 0, then you can think like we group them in the class 0 to 5. Yeah, multiple of 6, we group them. So this actually is a multiple of 6. Okay, we caution out the kernel, then we get is the set like this. Okay. And then
the quotient of 6Z.
Hmm?
6Z or
6 set is H, caution out the 6 set. The
the set you draw. What's the set you? The set you draw is the quotient of
set is this caution.
Why you erase it? That's not what you do.
Uh,
This one is quotient or secret?
Huh?
What do you like the set you draw just now?
the caution. Oh, the caution.
The quotient. Okay.
Wrap properly.
Okay.
Then this.
Yeah.
The 6 set is all the multiple of set.
Yeah.
Then you just add 0, 1, 2, 3. Get this. Okay.
The point of the hash here is this hash can be a proper subgroup of kernels.
Proper subgroup of kernel, you mean like
you
uh,
could just look at like
hash
0, 2, 4. Yeah. This could be one of the hash here. And then I think this is a normal subgroup of A. Yeah, I think this is like a you know 1, 2 that mod 3, but I guess that's
Right.
this one is a normal subgroup interview.
Oh, okay. You mean the 6 set is a multiple of set, right? Then
And you can look at the multiple of
look at the multiple. Maybe it's 12 subgroup.
oh yeah
12 subgroup. Just take the multiple of 12
yeah.
and then we caution out the 12. Okay.
It's a triangle like Z6 and Z12.
Triangle of set. You mean
Instead of because
okay. You have two.
you know you can have this triangle, right? This triangle Z6 and then Z12.
This
Triangle.
triangle.
Yeah.
Oh. Here.
G to Z6.
G to Z6.
Z12.
6 Z.
Z to Z6 and then the bottom one is Z12. Another triangle.
Another triangle.
Yeah.
Which tree are this?
This is a triangle.
This triangle.
Yeah. Draw another triangle.
Okay.
No need to just draw another triangle. Z
Okay.
to Z6.
Z
Take a different H.
to 6 Z6. How different H prime?
Yeah. No, you draw again the triangle.
You mean
Is there a triangle?
for this?
Yeah, draw a triangle for that. It's the same. You just change the bottom. No. Z6 is still there, but then your G mod H becomes Z12. Yeah. 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 And this is your theorem.
Yeah.
You take a different H now.
Different hash, but the hash is a subset of this kernel.
Yes.
Subset of kernel. Then
Here in this case, there's no isomorphism. But then in the previous case, there's an isomorphism between
these have isomorphism, but this, let me write down as an element. This element is 0, 2, like 11, I guess.
Yeah. And then there's a unique group homomorphism from Z mod 12 Z to Z6. You know what's that?
Say again, sorry.
Like what's that unique homomorphism?
Mm-hmm. The unit, right?
Yeah.
The unit.
Okay.
This,
Yeah, what's the phi tilde?
to say, because let's say between 6, 1, this 2, I think, is sent to this here.
All of them have the same.
Send the same 0 here.
Yeah. So
Inclusion.
0 and 6 have to be the same. What's that mean?
Right.
You send multiple of 6 to 0. What's that?
Yeah.
What do you call that?
Send multiple of 6 to
0.
0.
What do you call that?
This what?
Log 6. Log 6. That map is log 6.
Okay. Yeah.
You believe your theory.
Okay. Yeah, let me think. I a bit confused with that. And this is a tilde. So I send. You mean send the tilde? Define like and send to not 6. Let me think.
I mean, more precisely is you write it is the and write it as a equivalent plus. So yeah, you need to bracket that as well. No, everything. No, that doesn't make sense, right? You mod only can mod out integer, right? So you have to bracket everything. No, that one okay, This one is okay. I mean, the next one you should draw like bracket of
Okay.
12, meh?
6.
Yeah. But then you need to check the commutativity. You need to check the commutativity and check the uniqueness.
Okay.
Yeah, try and write this example down. You try to write this example down in your log center.
Okay.
Yeah, and then check the uniqueness, check the commutativity.
Unique and commutative. Sign up. Thank you. Thank you.
How many more is there?
A little bit.
A little bit.
A little bit.
How many slides? How many?
One more side.
Okay.
A little bit. Because chapter 7 is almost finished. And chapter 8, I taught example and then all use the same example. Okay. Yeah, after this is a definition. Okay, the definition just now we say every kernel is normal, right? One direction. And then now we take some other condition and then you can go back. Okay. Okay, this condition is a hash is normal subgroup, and then we have the subjective homomorphism pi. Okay, G to G modular H. And then the kernel pi is like H itself because we set the G to the GH. Yeah. And this. So G to GH, GH is the kernel, my kernel, right? Kernel is GH sent to the identity. Identity H is H itself. Okay. So the normal is a kernel.
Every normal
Every normal
subgroup. Every normal subgroup.
for it when I have this subjective homomorphism.
I mean normal subgroup.
Normal subgroup.
Yeah.
Okay. Every normal subgroup is a kernel. Yeah, last is last chapter 8. We will talk about the non-linear composition. Okay. We use one example and talk all of this. Okay. What this say? This say every group homomorphism G to G prime, you can decompose like this. We have the subjective, and then we have the quotient, we have isomorphism, and inclusion, injective. Okay. Why we want to do this? Because this is more easy to do like do this. Okay. Okay. Example. The same we take this is the take. Take this like buffer, more element can talk. Then the kernel we can take the multiple of 12. Then this is subjective is obviously because it's only 0 to 11. Okay. Then the image also sent like this. We can just take the identity map. Yeah. We do this just map from here to here is very hard a little bit, but we do here is easy after we decompose. The use of the decomposer. Okay. And this is more easy. Okay. And next we talk the presentation. What is the presentation mean? The presentation mean how we present the element, a group, group. Okay, how to present the group. Like the easy is the Z. We have many elements. Then we can do like a Z. Then we can group that. We can say 0, 0, 12, 24, like represent like this. Okay. The presentation, okay. And so on. 1, 13, and 25 like this. Okay. Yeah.
What's your FA? What's your R?
Um, R FA is like a free group. Free group mean I will not talk about this. Like if we have two element. The free group mean we have any combination, right? We can say ABB like this, AA, ABA, and so on. Like the relation, we take the relation like easy. We can say these two. We can represent them one. Okay. Yeah.
As a F, R.
Okay.
Yeah. You don't believe your definition, right?
Okay. Really.
Yeah.
Okay.
Right. Then definitely one is.
You see this, and then a free group like just that. Just do any combination. This. Now this is the relation. The relation is
What's your
A is Z. Everything. Everything. Then the relation is N mod chart. Okay.
N, maybe N.
Oh.
And optional should be
This.
no, it's just like N related to N log 12.
And
Actually, instead of FZ, actually you put F1 is enough already.
right. One.
Or you need minus one.
Minus one is
because
free group.
Give you the
Yeah.
So F1 is enough.
F1 is enough. Okay. Yeah. F1 is enough. And then the relation is this. So we G.
It's a subgroup, right? Can you write that as a subgroup?
Subgroup. Oh, okay. Yeah.
And what's
I mean, it's subgroup.
yeah, how do you write it as a subgroup? Because then it's just relation, right? You write it as a subgroup. What you say, or maybe how?
I mean, subgroup.
Yeah, how to write as a subgroup?
R is this.
Yeah.
Mm-hmm. Yeah.
Yeah. How do you write it as a subgroup?
A is a set and R is a subgroup. Sure. R is a subgroup of relation. I is a subgroup of relation.
R is the kernel of this. Kernel. R is a kernel. Oh, R is a kernel. Okay. Then I think you just write it as a subgroup generated by 12. 12Z basically. The way you write Z mod 12Z is exactly FA over R.
Mm-hmm.
You get what I mean? Z is the F1 and then 12Z is the R. Yeah, this is the subgroup event here. Relation. 12Z is a relation. Because you understand it as a kernel of the explicit subjection. Because your relation is n congruent to n mod 12.
Yeah.
Then this is the kernel of this surjection. And then this kernel is given by 12Z, multiple of 12Z. So Z over 12Z is exactly this FA over R.
Yeah.
So your R is 12Z. You write it as a subgroup. You understand?
The last one I didn't understand why.
Yeah, so 12Z is a subgroup.
Yeah. So 12Z is the subgroup of this.
Yes, correct. But then quotient out by 12Z is equivalent. You take relation and equivalent to n mod 12. The relation is the top there. And then how you write that write it as a subgroup is 12Z. Because the relation doesn't look like a subgroup, right? Is it a subgroup? How is it a subgroup?
The relation
Subgroup. Equivalent class. You have the equivalence relation. It's not a subgroup, right? This is the top one. No, this is a subgroup.
This is a subgroup.
The top one is not.
The top one is not a subgroup.
No, the above the relation you know.
This.
Yeah. This doesn't look like a subgroup.
This
Yeah, this is a subgroup. This is a subgroup, right? How do you draw that? It's not a set. It's just relation.
Okay.
Not a subgroup. Yeah.
R is
Here is a subgroup, but what you write down is not a subgroup. That's subgroup, right?
no.
How is it closed? How is it associative? How is it inverse? Where is it?
Is group one.
So Z is a subgroup because you can find inverse. You can.
And the relation
It's a subset of Z. That relation is a subset of Z. Right?
the relation is a subset of Z.
Yeah. Is there?
The relation is a subset of Z. Look, you mean that one is Z, right?
Sure.
Then
So what?
Okay.
I mean, there's a relation. There's no element. You cannot just see n one. You are looking at the n equivalent to n mod 12. The whole thing.
But the whole thing, okay. But can I write like this? The set, write the n.
You can, but then that's not what you want, right? You're telling people what's the relation, right? You're not telling people what the set is. I mean, well, I mean, to tell people relation, you can tell people the what we call that binary, not binary, the tuple, right? For example, 0 and 12 is the same. And then 0 and 24 is the same. But then there's not a subgroup either. There's no subgroup of Z. So my question is, how do you view relation as a subgroup?
To view the relation is the subgroup.
Yeah.
You mean this must be a group? Then we can write this. See how to relate the relation to the subgroup. Change to another ways to say. To your question,
my question.
change another ways to say.
Change another way to say. So okay, define subgroup of relation.
Find subgroup of relation.
You write in your
Okay.
and define subgroup of relation.
Subgroup.
How many more slides?
Just like here.
Any?
Okay. Like
second isomorphic control.
this last one. I think it's this you can. Okay. I think we can just see clearly now. Okay. The G quotient H. Yeah, we can think like this. G quotient H. Like the element GH. Okay. Then blah, blah, blah. Okay. And then the divisor is also more quotient. Okay. More modular. Then next is the N quotient H is NH. Okay. Yeah. Then this quotient, this is GH. NH. Okay. Then we say before this, we can write like GNH. Okay.
Because
The left, let's say the left offset, left relation. GN. HH is in H, right?
Huh?
HH.
Yeah. And then this is GNH.
G, okay.
To help you explain.
Okay.
You swap now, right?
Yeah, so
GHN H equals to GNH equals to GN.
okay. Okay, thank you. Then this is also G and quotient H. Okay. Now we want to check this isomorphism to the G modular N. Okay. And the detail I don't talk like idea is like this. I'm going to check. This is okay. This is
Wait, G mod N. Why is it GH again? Is it GN?
GN. Thank you. H G N. Okay.
You know that map? What's that map? Map of that isomorphism. You write down the map. Maybe you can check it.
Okay. So I think this is HF4. Let me think.
I think the first equality looks a bit weird.
This. Hmm. This.
Because because if you think about it, your G mod H is GH, right? But then N mod H, you should think of it as a group. So maybe you should write like GH and then N mod H.
GH and then H.
Because if you use the same logic you do GH, right, you should get. Maybe we can end here, but then
Okay.
like your logic is like G mod H. I write it as GH, right? But then G mod H mod N mod H, this one should be a group.
Yeah.
Then why not you write GH and then N mod H? Isn't it? This is the logic.
Yeah.
But instead you write GH and H.
This also a group. This also the set. NH is.
Yeah, you should write it as a group one. Here's is a group one. This one. This one should be this one.
Yeah.
This is a group element here. This one also element. Why not write in this one? You write in this one.
This is correct, but this implies this, right?
But if this implies this, why not I just write like this? Can I write like this? Different, this is a different thing. We are not looking at we are viewing this whole thing as an element.
Yeah.
This is definitely set this thing, but then we view it as a single element.
Okay.
We are not separating down every element. You get what I'm saying? Is this whole thing form a group? Not this form a group. This cannot form a group. Is this form a group? Is G1H?
Yeah.
This thing form a group, but then this doesn't form a group.
Yeah.
Similar here. Why you break it down? Why you break this thing down?
Oh, okay.
This one make more sense, right? You see, kind of like cancel and.
I know, but I think very long time. But why I can cancel so?
Yeah. Then that's mean you need to this write down this map only you know. Otherwise you don't know. You need to write down this map here. I believe it's just this thing but then you need to show isomorphism. But before that, I think you need to show well-defined first. Well-defined and then isomorphic and then okay. I think it's
Okay.
okay.
Done.
Done.
And this similar, like how to do like this.
Yeah.
Just
Composition is not position. No.
yeah.
Yeah.
Okay.
Pretty important, and later we'll use this information in one more the result.
Okay. Thank you.
For question.
Oh.
You guys like record? Huh? You have paper? Okay.
It's closer.
Closer. No question. No question. No question. Maybe we'll break first. Huh? Break until 3:20.
I only have 30 minutes today.
Today. We can continue on Friday.
Then I can finish my presentation.
Too many questions from me.
I have a question. What is there?
Yeah, you just
I can write the whiteboard.
Tissue.
Okay.
You need to get a tissue.谁猜的？
谢谢。
谢谢。
你要用 whiteboard 啊？OK。OK。
Should I start now? It's 3:20. Good afternoon, everyone. I'm Yu Hang, and my presentation supposedly will be divided into three parts. In the first part, I will discuss about Lagrange's theorem and give some direct applications of Lagrange's theorem. And in the second part, I will discuss about group actions. I believe that everyone has learned before group action in their undergraduate studies, but maybe on this Friday, I will give two equivalent definitions of group actions, one in categorical terms and another in the usual sense. And I will show that these two definitions are equivalent. And then in the third part, I will introduce an object called any arbitrary category called group object, which exhibits similar properties as group in the usual set theoretical sense. And yeah, without further ado, I have 30 minutes left, so I think that I will talk about Lagrange's theorem only today. But so the Lagrange's theorem. First, recall that notation G/H, where H is any subgroup of the group G, is the set of left cosets of H. Since that we only assume that H is any subgroup of G, so this might be just a set, not a group. But if H is normal, then this is a group. So next, the set of left cosets of H from a partition of G. So remember these two facts. Before I talk about Lagrange's theorem, let's prove a simple lemma first. Lemma. For any G in G, the function defined by H, the domain is H. H is a subgroup and to GH, such that it sends every H to GH is a bijection. To prove that a function is bijection, we need to show two things. First, surjectivity. But surjectivity is very obvious since that it follows directly from the definition. Send every H to GH, so every GH has a H. So surjectivity is by definition.
I think you take G inverse.
What?
You should take G inverse to recover your H.
No. What do you mean? Right now, I'm talking about surjectivity.
Yes. So
no, I mean it's very obvious that you send every H to every GH.
But then
so
from GH, how do you recover your H?
So let's say we have a GH. Then simply let's say this function is 5, then 5H you get GH. That's all. It follows directly from the definition. So okay? You don't think that it follows from the definition? Remember that G, these are a series of functions. We have for every element G, we have a function. Is it okay?
Yeah, I mean okay. So maybe this GH has a form of small g times small h, right? But in reality, right, this GH, right, could be combined into some other element. You get what I mean?
It doesn't matter. Since that what I'm talking about, you are talking about the well-definers of this function. Is it?
Talking about no, it's not well-defined. It's just that there's a systematic way to extract H. So I mean, like,
but this is not. I'm not sure what you're talking about. But
I mean, like, okay, what am I talking about is very easy. So surjectivity is for every element in GH, right?
yeah.
You have an element in H such that F of
It's correct. That's defined.
H is GH, right? So, okay, I mean, you can abstract H in this way easily because your GH, every element can be written in the form of little g H.
Yeah.
Yes.
This is a definition.
Yes. It's okay. It's okay. I'm just trying to tell you, there's a more systematic way to extract this.
No, it doesn't matter since that this is just a lemma to prove the Lagrange's theorem. So I won't focus on this because I have because I need to prove the Lagrange's theorem is the main topic of today.
No, it's okay.
So this lemma is just like a.
It's
I
okay.
didn't write it out very rigorously because it's just for.
I understand. I just want to ask whether you know the technicality or not.
Okay.
I just wanted to ask if you
Oh.
know that. Yeah. I just wanted to test if you know
Yeah.
the technicality.
Never mind. It's okay. So never mind. I only have. Yeah. We can talk about the.
No. I'm very quick one. I'm very quick. You just take G inverse.
You take G inverse. What do you mean?
On any element on that.
GH. I take G inverse.
Then you can recover your pre-image. Then you can take G inverse of that thing is your pre-image. Take that as your pre-image.
Finally, G and G, the function define H, G inverse. I can get this, yeah? What? It's okay. I think it.
这个是找得到的。这是找的，因为
Yeah.
我的假设是说假设找不到。
It's okay.
Then 就转 G。
Never mind. Let's move on. Injectivity. Injectivity, we need to show that if GH1 is equal to GH2, we need to show that H1 is equal to H2. But since that G is a group, so cancellation laws hold. Also, H1 is equal to H2. Or you can take the inverse.
This is what I said just now.
Yeah, so that's why.
So you just agree?
No.
What no? You agree? You can agree. Why cannot?
But I will say that there's nothing to disagree. You know.
Huh?
Like
no, I'm not disagree you.
No. I mean that the thing that you are saying, there's nothing to disagree.
I know.
So I don't know why we have that conversation. But
no, because it's like you didn't disagree, but you didn't agree as well. So this is.
Oh, you want me to agree?
Of course.
Okay, I agree.
If you don't agree to something is true, then this not disagree doesn't mean agree.
Okay. Yeah. Okay, so by this lemma, we've shown that for any G in the group G, we have a bijection between H and GH. So now we can prove the Lagrange's theorem. Let H be a subgroup of a group G. Then, of finite group. Then the order of the group G is equal to the order of G quotient H times H. So how do we prove this? First, if G is a group, let's draw a diagram. Suppose that this is a group G. This is just a sketch of the proof. And remember that the set of left cosets of H form a partition of G, and this is the set of all distinct left cosets of H. So you can this left coset. And H, we have shown that there exists bijection between each GH and H, which means that for any G in G, the cardinality of H is equal to GH. So which means that every left coset have the same number of elements. So simply the number of the whole group is the number of left cosets times the number of elements in each left coset. So this is the sketch of the proof. So let's look at one proposition. of a direct application of the Lagrange theorem. Let G be an element in G where G is the finite group. Then the order of G divides the order of the group. This is simple just by note that the order of this element is equal to the order of the subgroup generated by this element. And since that this is a subgroup, so this is this, and so this divides this. That's all. Do you have any question? If not, let's move on to the second application. I think it's no. It's called Fermat's little theorem. Let P be any prime integer, and let A be any integer. Then A power of P is congruent to A mod P. So I will prove this by a case-by-case basis. First, we show, suppose that A is a multiple of P. This is a simple case. What does this mean? This means that P divides A minus AP. But what is A minus AP? A to the power of P. It's, you factorize A out, you get 1 minus AP minus 1. But A is a multiple of P, and P divides this. So P divides A. So P divides the whole thing. So it follows immediately from this. Second, if A...
Wait. So the first case is 0, right?
No, A is a multiple of P. A is an integer. If
multiple of P, so it's 0, A mod P.
Yeah.
Yeah, so the easy case is because both sides is 0 mod P.
But if you since that we are talking right now, we are talking about two integers P and A in integer, and I translate it to this is A minus AP. The definition of this statement is A minus AP is divided by P. And what is A minus AP? A minus AP, you factorize the A out, is A times 1 minus A power of P minus 1. And since that A is a multiple of P, so if you divide A by P, you get some integer. So it's the simple case. So
you are saying that A minus AP is also a multiple of P, right? This is your conclusion.
But it doesn't matter. It's a fact, but it doesn't. No. It's not the result that we're looking for.
It is. It is. That's what you written down. It is.
A is a multiple.
You are trying to prove that AP minus A is...
Yeah. Sorry.
Yeah.
It's kind of confusing. Sometimes you say one divides another and again, and it's a multiple of, it's kind of confusing sometimes.
And then that's the goal, the result you want to prove.
Yeah. Sure. But that's the simple case. Now, let's look at another case. How many minutes do I have? Oh, 16 minutes. Second case. So since that we assume that A is a multiple of P, now suppose that A is not a multiple of P. If A is not a multiple of P, what does this mean? The congruent class AP is not equal to 0. Because if A is equal to this, then A must be a multiple of P. So can you connect the dots? Okay. So if A is not equal to 0, it implies that this is in the multiplicative group of modular P. Since that P is a prime integer, so this is a group. Okay, so what's the order of this group? Does anybody know that? What's the order of this group? The order? Yeah, it's P minus 1 because the element is 1, 2, until P minus 1. The order of this group is P minus 1. And using this proposition, which the order of the element is the order of the subgroup it generated, which means that the order of this G, the order of this is the order of it, the cyclic subgroup it generated, and this is the subgroup of G. And it's the subgroup of this one. So which means that this divides this. Is it clear? Since that the order divides P minus 1, which means that AP power of P minus 1 is equal to the identity. If we multiply both sides by P, we get AP power of P is equal to AP, which is the result we are looking for. This one. Okay.
Okay, there's some add on here. Maybe you can try and prove that why Z mod PZ star is everything other than 0. So meaning you can try and prove that y 1 up to P minus 1 is invertible in Z mod PZ.
Yeah.
Because it's not true for any Z mod
P. If P is in prime number, only P is prime number, that only this will form a group.
Yes. Maybe you can try and prove.
Yeah, this is in the subgroup section. So I'm going to talk about this right now.
You guys prove this in the subgroup section?
Yeah, it's in the textbook.
Okay.
It's shown, so I want you to read this right now. So I think that's all for the first section.
I think he skipped one. 但是没有讨论到。哎，别 no I want to talk about it.
I remember it.
你知道的，你想那个 Z mod PZ
就是其他的 other than 0的 element 是一个在这个 set 里面。
only prime number
for that mod PZ non-zero element are unique. Proof from 你没有
别讲，
你没有背，
是我真没有看。
你会写没？我记得你是背的这个。Yeah， 你会写吗？
If you want to define this, it's a little bit troublesome because I need to define what's multiplication in.
Yes.
You need to define the value definers, and from that on, you need to work on a lot of details. Only that you can assume that you can show that it's GCD, P and not N. This one show that they are relative prime. Only that it forms a group.
So actually, those proof you don't need to prove. Those proof you can infer from number theory. But then the result stuff maybe.
Sometimes we need to assume something is true because it.
No. I'm not asking about proof sometimes, but then the maybe some result you need to recall there.
Yeah. So let's move on to the second section, which is chapter 2, section 9 of Paulo Alves' algebra chapter. So we'll talk about group actions. So we have two definitions of group actions. Definition 1. and an action of a group of, over here we first assume that C is any category. Let C be a category. An action of a group G on an object A is a homomorphism.
Wait, let me stop you first.
Okay.
You need to give me a chance to stop you.
Oh.
I can stop you.
Yeah.
I can extend your time as well.
Is
So
it? Oh,
I'm okay.
really?
Maybe like extend
Because I already timed my presentation.
Sure.
It's in under only 1 hour.
I can grant you the privilege.
Oh.
I can grant you.
Oh,
I mean,
really?
If I stop you, I give you a chance to answer.
Okay.
Yeah. So you don't need to rush on. Obviously, you try to keep your stuff in 1 hour, but then if I stop you, I make you longer. I
Oh,
won't
okay.
force you like finish in 1 hour. I mean, like this happens to 3
Oh.
hours. Right. So you don't need to scare like I extend your time because I can extend.
Oh, okay.
Yeah.
So what's the question?
No question.
Okay. So
But later will happen. Later will happen.
okay. So it's a homomorphism from sigma. It's a homomorphism. We name it as sigma from a group G to a set of automorphisms of category C of the object A. First, note that the definition we use homomorphism, but homomorphism we define it from a group to another group. G is definitely a group since by definition it's a group. But how about this? Is it a group? What and why? So what is this? Does somebody know what is this? The set of automorphisms of object A. What is this? What is the element of this set? Yeah, isomorphisms. So isomorphisms, you can show that isomorphisms satisfy the 3 properties of group. Identity exists since that it's by definition of category. Inverse, since the isomorphisms has inverses, so it satisfies the inverse property. And the third property is again iso-associativity, which is true by the definition of category. So this is a group. Okay, so the second definition, let's move on to a more familiar territory, which is the category set. The category set. And action of a group G on a set A is the function rho GA to A defined by it satisfies 2 properties. First, rho E of any A in A, rho EG is the identity of G is equal to A. And second, rho for all A in A and for all G1, G2 in G, rho G1, G2, A is equal to rho G1, rho G2A. Some of you may be more familiar with this G1, G2, A is equal to G1 bracket G2A. But since that this is the first time I introduced to avoid confusion, I will use rho because if you write like this, the action and the binary operation on groups will have the same way of writing it. So let's stick with rho first. So right now we have 2 definitions. First is in the category set, the second is in the in any category. So is it true that these 2 are equivalent? So let's look at. I will show 2 to 1 first. This is 2, and this is 1. For 2 to 1, we need to construct an homomorphism from G to the set of automorphisms. since that right now our category is set, so what are the elements of this group? This set. If C, the category is in set, what's the element of this set? It's an isomorphism in, what's an isomorphism in set? Yes, bijections. So this is the set of bijections of A. So if you remember what's the definition of a symmetric group? It's the symmetric group. Like the group of permutations, bijection can be thought as arranging all the elements in a new way. So the collection of bijection is the symmetric group. Okay, so we need to construct a sigma from G to this, and this, the element is functions, not the elements like you may think of. So this is, so we need to, so define, maybe we can define the element over here by sigma G for any G in G. Sigma G is defined to be A to A, the element of this one. Since that 2 to 1, so we have a row right now. Row sigma G A, we define it to be row GA. First, we need to show that this, for all G in G, this is a bijection. So to show that bijection for all G in G, I will show it by showing that it has an inverse. Since that it is defined over G, so we have G and we have G inverse. And we need, okay. So again, row G, this is this. And what is this? This is row G inverse A by this definition. And what is this? Again, applying the definition again, it's sigma G. Sigma G is, so it's row G inverse A. But by the definition 2 of action, this, we can combine it to become this. So this is row G inverse A. And G inverse, we get the identity. And by property 1, we get A. To show that a function has an inverse, you need to show both sides, right? But since that we only assume G is an arbitrary element in G, so you can somehow like replace this G inverse. This is not rigorous, but something like this, and you automatically satisfy the whole equation.
Oh, you just do another computation.
Yeah, but you don't need to write it down since that G is arbitrary. My point is this. So this, for all sigma G regard bijection, now we need to construct a sigma. We define sigma from G to this one, set A, by sigma G. We define it to be this function. To show that sigma is a homomorphism, we need to show, recall. Let's say phi is a homomorphism. Phi AB is equal to phi A, phi B. So for this one, we need to show that sigma G1, G2 is equal to sigma G1 composite with sigma G2. Since that the relation in this set is composition, these two are functions. To show that two functions are equal, we need to ensure that they agree on all values on the domain so that they can be equal. So let's say we let A be an arbitrary A. This function G1, G2, A. This function, by this definition, is sigma G1, G2, A. And by this definition, sigma G1, G2, we get row G1, G2, A. Using the second property, we get rho G1, rho G2A, and rho G1, G2A, and what's rho G2A? Rho G2A, by definition, it's sigma G2A. Rho G1. And again, what's the definition of sigma? You can revert back to again. So it's G1 and this is A. So this is the composition function. So sigma is a homomorphism of this. Oh, should I stop now or I show the other direction? Maybe I do a quick one. I show the. Oh no, it's okay. I think that I can resume next class since it's 3:50 already. Do you have any questions?
Yeah. Maybe I'll come up with the group assignment. Not group assignment, the assignment of chapter groups. Maybe this week. And then maybe there will be 2 weeks. 2 weeks deadline. Yeah. Okay. And then after Yuhan presentation, then I'll resume my lecture on groups. And then after groups, we will do rings. And then after rings, I'll do module. Other module, then we'll do homological algebra. Huh? Yeah. Hopefully rings is relatively faster. Yeah. Hopefully. Depends. So like since you already like go through like question from me, right? So when you prepare the next presentation, make sure you think about this kind of triviality. Either you can present it or you quickly comment on it, or be prepared when I ask some triviality. Yeah. Because this is one way I want to test you whether you know what you are talking about or not. Understand what I say? Yeah. Okay. Okay, good. Thank you very much. See you on Friday. Maybe you need to erase it. Okay, yeah. Oh, give me your marking, huh?